is a familiar name for the physical listed artist. I would say that you can't go to 3 physical oceanography lectures before someone consecutively before someone mentions Arnold Arons. Arnold Arons circulation, the abyssal circulation, basic dynamics of abyssal circulation in the world ocean. And so, and that work dates back to the 50s, and I was surprised to find out that you did acoustics earlier than that here, apparently in this building. Dr. Arons is a professor emeritus at the University of Washington, and previously has taught at Amherst College and Stevens Institute, and has received numerous awards for physics teaching and research from many societies, fellow of a couple of societies. So it's a great honor to have you. So we're eager to hear what you have to say.
Okay. Currently a trustee of the place.
Since I'm going to have the temerity to talk about shallow water acoustics, I feel intimidated by the presence of so many experts. As you obsolesce as a scientist, if you live long enough, you turn into a historian. And I guess that's what's happening to me. So let me start with a few remarks about what transpired here during the Second World War, before most of you were born, I guess. That's a preliminary to the work that I will be talking about, in fact. I assume most of you know that prior to the Second World War, this institution was essentially a summer operation. It had virtually nothing in the way of a permanent staff. Bigelow was director out of his real seat at Harvard. Columbus Islin was a full-time employee, and Bill Schroeder, the ichthyologist, was sort of permanent caretaker. He took care of the place when it was locked up during the winter months. And the summer operation was very much the way MBL used to be. Namely, people would come from the academic institutions. Islin essentially conducted whatever physical oceanography was going on. I believe I'm not very well versed in the details of what went on then, because that was before my own time. But one of the prominent biological enterprises was microbiology under Selman Waksman. He got the Nobel Prize for the discovery of streptomycin. His headquarters were Rutgers. And he came here with students who became rather distinguished coterie all around the country. So that was the general atmosphere of the institution prior to 1941. Now, with the advent of the Second World War, beginning a little bit before Pearl Harbor, but then developing rapidly after December 41, there were 3 principal operations that came into being on a full-time, year-round basis here. One was in biology, and incidentally, at that time, the only building that the institution had was this one. It was here. There wasn't none of the other buildings existed. Out on the dock, there was a little brick house we called the pump house, which had the pumping machinery that supplied the saltwater tanks for biological work in the building. That's all there was. Now, the biology, group in biology was a substantial one under Alfred Redfield and Buck Ketchum. A number of other people whose names I don't recall offhand, although they've come back after an interval. The problem was bottom fouling in ships, which was a serious wartime problem. Incapacitation of ships that should be active because of biological growth on the bottom. And that group developed the copper-based anti-fouling paints that still persist in the maritime practice. They occupied the second floor. The first floor was occupied by Morris Ewing and his group, who were concentrating principally on underwater sound. Al Vine was then a young graduate, one of the leading members of the group. Joe Warzel, who left here with Ewing subsequently, but they were the key members. They discovered the SOFAR channel and set up the system for triangulating boats in distress after sinking of merchant shipping and so forth. And they greatly refined and improved the bathythermograph, which had been started by Athelstan Spilkhouse at MIT. And they did extensive work on ray tracing, ray propagation. Al Vine spent a good bit of those war years visiting active submarines around the war circuit and instructing them on how to use shadow zones to hide from sonar detection based on the ray tracing insights and so forth that they were gaining here. So that was the enterprise of that group. And finally, there was sprinkling of smaller projects that I won't dwell on, picking up the big ones. The third group was the one that I was involved in, and we were the last of the big three groups to come to the institution. Our program was started at Harvard. I was then a graduate student of E. Bright Wilson Jr.'s. The Wilson, who had been doing infrared and Raman spectra, structure of polyatomic molecules, had been commissioned from Washington. The big enterprises set up in Washington were the OSRD, the Office of Scientific Research and Development under Vannevar Bush, which had overall purview of the of scientific engineering, technological development in the war effort. And then there was a science operation, the NDRC, the National Defense Research Committee, under James Conant, who was president of Harvard. And the NDRC had a number of divisions: acoustics, explosion phenomena, electricity and magnetism, mine warfare, there were all those problems of magnetic mines and whatnot. The explosive division was headed by George Kistiakowsky, the physical chemist from Harvard, and he entangled his colleague, Bright Wilson, who was then a junior member of in physical chemistry of that department, to abandon infrared and Raman spectra and to turn his attention to explosion phenomena in water and air. And I was then a beginning graduate student of Wilson's, and had started to modify the infrared spectrometer for the purpose of measuring absolute dipole moments of polyatomic molecules. Well, that went by the boards in a hurry. Wilson called in all his graduate students and announced that he was switching to explosives research. And invited those who were willing to join him to stay, and told the others who didn't want to do that kind of thing to find another thesis advisor. So, well, actually, all of us stayed. This was, to pinpoint it, 3 months before Pearl Harbor. Now, we started on working on the explosion phenomena immediately. There was very little known about the shock wave generated by an explosion. You see, it took obviously rapid instrumentation in order to detect and see what was going on. Attempts had been made during the First World War, which didn't really get very far. And so here in 1941, the question was, what is the shape of the shock wave? We knew it was approximately exponential, but what was the decay constant? How sharp is a shock front? How do the amplitudes scale? And then, of course, the phenomenon goes beyond that, because once you have a detonation take place, the gas globe expands and overshoots and comes back, and you get another pulse, and there's the hydrodynamics of all of that stuff, all of those phenomena. Now, in 1941, what we had available for instrumentation was the Dumont 208 oscilloscope. It was the first oscilloscope in which you could hope to get, or you had to modify the electronics because the sweep on it was nonlinear. But if you developed a better electronics, you could get a linear sweep, and the amplitude electronics were reasonably linear. They needed calibration, etc. But it was a device with which you could begin to do quantitative work. And I found myself, rather than monkeying with an infrared spectrometer over in the mineralogy lab at Harvard, learning how to use a diamond saw and cutting crystals of tourmaline. Now, we selected tourmaline as the piezoelectric device for getting a signal for a number of reasons. The obvious thing to most individuals would have been quartz. But quartz is not hydrostatically sensitive. In order to get a piezoelectric, if you subject quartz to a hydrostatic pressure, you get no piezoelectric signal, no charge. Quartz is sensitive along the principal axis. It's also sensitive along another, but only unilateral. And so if you wanted to use quartz, you'd have to put it into a housing. And if you put it into a housing and subjected it to a shockwave pulse, you were going to get serious ringing. And so what was indicated was something hydrostatically sensitive, and tourmaline is hydrostatically sensitive, and just about the same sensitivity as quartz. There's no real distinction between. And so I was assigned the task of creating a piezoelectric gauge that we could attach to the oscilloscope. Bob Cole, who subsequently became a trustee here, he was senior to me. He took on he was a very skilled electronics man, as well as high-powered theoretically, and he undertook the task of generating the electronic equipment. I was assigned the task of creating a gauge. And I won't go into the details, but what was necessary was to cut tourmaline slabs, plate them so you had a conducting coating. What we did, one slab was of limited sensitivity. What we did was pile up 4 slabs in parallel, so you got more charge for the smallest possible radius. But you had to provide conductive coating, cement them together, provide a waterproof coating that would stand up under shock wave pressures attached to a cable and so forth. So that was my principal enterprise, and personally, with a lot of other stuff going on. We started verifying the techniques in a tank about 5 or 6 feet in diameter and about 6 feet high in one of the laboratories at Harvard. And we shot blasting caps and got a lot of complaints. And it was obvious that to go beyond blasting caps, this kind of work could not be done in the middle of Cambridge. And so Bright was searching around for somewhere to go where we would have access to open water, and it had to be more than just a pond kind of thing, because there loomed in the future the necessity of testing full-scale depth charges and things of that variety. And so Bright discovered the Woods Hole Oceanographic Institution and approached Columbus Islin on whether setup could be brought here, and Columbus said, why, of course, come along, and the operation was moved here. And our group was increasing rapidly in size, and we occupied the 3rd floor. My original office was up in that extreme corner of the 3rd floor. I vividly remember before we actually moved, Bright and I came down here by car. Bob Cole, who had been setting up the electronics system out at Brewston, Pennsylvania, moved here with the electronic equipment. Bright and I came down from Harvard with the gauges. We put the equipment out there in the pump house and rigged we had a steel ring on cables which we lowered off the dock and shot our first charges of maybe 100 grams of explosive instead of a blasting cap. What I remember about that time was that it was about the middle of February 1942, and there was a week of weather in which the temperature did not fall below 0 Fahrenheit. It did not come above 0 Fahrenheit. It stayed around 0. Now, I've never been so cold in my life, working out there in the dock. When we raised that rig out of the water, icicles formed from the salt water. So, and well, we learned to dress more practically on subsequent occasions. But anyway, the group moved here, and we operated throughout the Second World War. The problems were, my personal concern, my assignment was the physics of the explosion. the scaling of the shock wave, the pressure amplitude. Acoustically it should be 1 over R, but with finite amplitude you get dissipation. And the radial dependence is 1.13 rather than 1.10. And that incidentally extends over a phenomenally large range, down to pressures at least of only a few pounds per square inch, almost acoustic levels, but it continues as a 1.13 straight line semi-log plot as far as you can go, as far I was able to go. One of the things we were looking for eventually was, does it change the slope? And we never found any change in slope. The kind of thing we had to work on from a wartime practical standpoint. The physics was obviously underpinning. The questions were, what are optimum compositions for explosives? TNT was becoming old hat. There were new explosive compounds, HBX, pentolite, various other things. You enhanced the pressure pulse by adding ammonium nitrate, aluminum, etc. So ultimately, for manufacturing purposes, questions were what mixtures are optimum. And this was obviously a serious economic problem. You were determining the national wartime effort on optimum explosive compositions. We had a casting house over on Nonamesset Island, plus magazines where we stored explosives. We leased the northeast end of the Nonamesset, all the way down to where the woods began, the end of the meadow. We had a leasehold from the Forbeses. And so the delicate work was done over there. And in the meadow, between the house that you still see in the woods, they would deliver full-scale depth charges to us, bounce them on the dock out here, put them on a boat, take them over and bury them in the meadow until we took them out. We set up a larger boat, a Gloucester fisherman, to shoot larger charges out in the Sound. We did the small-scale work right here off the dock. The experimental compositions were poured over on the island, etc. We studied the pulsation phenomena. We studied the surface effect. We had a group under Paul Fye studying the collapse of cylinders under explosive impact, in other words, models of submarine hulls and the scaling problems that went with that. That was the nature of the enterprise. And those were the 3 big operations that went on here during the war. For some reason or other, it was out of the, Alfred Redfield and Buck Ketchum were permanent staff members here. They were here all the way through. But out of the explosive group, there came 6 individuals who entered the trustee structure of the institution. Bright Wilson was the first one. He was a longtime trustee, member of the executive committee. Spike Coles, who was junior to Wilson, he was one of the research supervisors. He supervised the full-scale work out in the Sound. He went to Brown as a physical chemist. He became dean there, quickly became president of Bowdoin College, and subsequently president of the Research Corporation. And he was a longtime trustee. Spike chaired the committee that created the joint graduate program with MIT. Bright Wilson was taken away from here. Kistiakovsky left Division II of NDRC to head the explosives work at Los Alamos, and Wilson was made head of Division II, the Explosive Division at NDRC. So he was succeeded here by Paul Cross, who was professor of physical chemistry at Brown. And Cross subsequently became a trustee. Cross left Brown, became head of the chemistry department at my place, University of Washington. Then he became head of the Mellon Institute of Pittsburgh, and he sat on the combination of Carnegie Institute of Technology and the Mellon Institute to become Carnegie Mellon University. He was a trustee. Bob Cole went to Brown, made a career in dielectric phenomena, and was a trustee and member of the executive committee. Paul Fye became a director, and I'm the sole survivor of that crowd. I became a trustee in '64, and I sat with Spike on the committee that generated the graduate program with MIT. So that explosion phenomenon group had extensive connection with the institution, as you can see. Well, now let's get down to some science. These are just qualitative stories. I got into oceanography by staying on here, coming back. So I went back to academic work, but I came here summers with students, and I knew nothing whatsoever about oceanography. I'd hardly heard about it before, but what I did initially was simply to continue work that we had started during the war years. There were questions left over, and I had funding for that. There was money left over, actually, from the war year. And so what I proceeded to do was to continue looking at some questions that had puzzled me from the previous period. One was that scaling business that I've already referred to. How far does that pressure scaling law go? And as I said, it went as far as I was able to follow. Then another question that I had in mind was, what about the shock front? High frequencies are attenuated more strongly, as you know, than lower frequencies, and quite significantly more strongly. If you think of a pulse like that as having a Fourier spectrum, the high frequencies are associated with the abrupt rise. And if one goes out far enough, one ought to begin to see some rounding of the shock front. And so I thought I'd start having a look at that. And the ship available to me at the time was the Chain, which some of you remember, and a small boat. And what we did was to use the techniques that we had developed back during the war, the tourmaline gauges, cables, oscilloscopes, but to go out in the Sound and start increasing the range, looking at what happened to the lowest peak pressures we could go to. And let me show you some of the kinds of records that we developed. These are oscilloscope traces. What we have here is the shock pulse, the leading edge, typical shape, that shape is very well represented by an exponential decay until you get down about one time constant of the exponential, and beyond one time constant it's slower than the exponential decay, but the decay continues, and mathematically we treated this as a exponential shape with an infinitely steep front. But what I was looking for in going out to long range was visible rounding off of that front, which in fact we did never observed. Now, we established quantitatively, I mean, we needed to know the range, how far we were from each other. We knew the depth of water, we measured that. The bottom out there is slowly undulating, fortunately, so that I mean, you get differences in level of 5 or 6 feet. Getting treated as we treated it as a plane surface as we did the free. Now, the kind of thing that we observed as we went out to longer and longer ranges is shown here. This is the angle of incidence at the bottom is indicated there. It's 57 degrees. Angle of incidence for a ray. And this thing here is the surface reflection, the rarefaction, inversion phase, and that's the bottom reflection, which is pretty much like the original shape, lower in amplitude. But then, as we went to larger range, here's the incident shock, and the bottom reflection looked like this.
What depth was the receiver?
The receiver and the charge were placed at mid-depth. They were always at mid-depth. Now here was the bottom reflection, considerably bigger than it is there, altering in shape, at least the amplitude of the incident pulse. And see, these are increasing angles of incidence. This goes on. That peak gets sharper and sharper, and it frequently exceeded the amplitude of the incident peak. Now, the first thing that when we first saw that effect, we started tearing the equipment apart, worrying that there was something wrong with instrumentation. But that turned out not to be the case. This was for real. And so the question came, what's the physics? What's going on there? And quite puzzled about it, but the one thing that I learned while I was in that game was that you could find practically anything in Rayleigh.
Yep. That's for sure. Keep that saying that Rayleigh thought of everything.
That's right. And so I went back to Rayleigh and I examined reflections. And of course everything in Rayleigh is in terms of sinusoidal wave trains. He never thought about pulses. But the story is there, and the story is as follows. I won't go through the mathematics. I'm going to talk about the physics and the phenomenology, and if you want the full dress treatment, I will give you the references, but I'll talk about the physics. If you look at Rayleigh on reflection from an interface with the usual boundary conditions, continuity of pressure, continuity of particle velocity, normal distance, you find that when you have a reflection from something like the seabed, namely an interface with higher velocity of propagation, there's a critical angle for total reflection. But associated with that critical angle for total reflection is the phase shift of the reflected wave relative to the incident. And the phase shift depends on the acoustic parameters, on the densities and the sound velocities only. Okay, now I have been thinking in terms of pulses and occasionally in terms of Fourier spectra. And what I realized was that that phase shift was bound to have serious consequences. You see, in ordinary electronics, we have a phase shift for an input signal, but the phase shifts are proportional to the frequency. When you describe your sinusoid at e to the I omega t, and then you have a phase shift which is also e to the I omega, e to the I phi, but phi is proportional to omega. You see e to the I omega t and e to the I omega with a phase shift, the t and the shift couple, you get the same time delay for every frequency component if the phase shift is proportional to the frequency. Then you have no distortion. But in this physics, you see the phase shift turns out to not to be frequency dependent at all. It's a function of the angle of incidence. It's zero at the critical angle for total reflection, and it's 180 degrees for grazing incidence. The phase shift varies from 0 to 180 degrees as you go beyond the critical angle for total reflection. And so for every different angle of incidence beyond the critical, you have a different phase shift which you would have to apply to the spectrum impulse. And the question was, what would that look like? Now, what we did was to take the exponential pulse with an infinitely steep rise, 0 time interval, the shock front. Actually, of course, the time of rise of the shock can't be 0, but it is fast. It's a matter of a few mean free paths in the liquid, as it was subsequently determined. So it is plenty steep without being 0. Fourier spectrum, the exponential, and applied the phase shift and recombined. Now, when you do that, you encounter a strange kind of function. It was strange to me, although it was well tabulated. It was in Janka and Emda with all the other functions like Bessel functions, Laguerre's and whatnot, called the exponential integral, EI, exponential integral, function. That's what turns up in this case. Nowadays, Yanka and Emda is dead, I'm sure, and all turns up in mathematical or whatnot. But we had to go to the tables. Now, when we go to the tables, what we get are these graphs. That's for an angle of incidence before the critical. You get a reflection that is the same shape as your incident pulse. Now you get beyond the critical angle. This is for a phase shift of 15 degrees. Phase shift of 15 degrees, angle of incidence of 71. And now with that exponential integral in there, applying the phase shift, you see you begin to get this kind of thing, and there it is. And now we're at a phase shift of 30 degrees, and here is the bottom reflection, there is the shape that you would expect. And that amplitude can easily be higher than the amplitude of the incident pulse, because the exponential integral at 0 has a logarithmic infinity. For mathematical discontinuity, you have an infinity. And if it's not really discontinuous, then you don't go to infinity, but you can get plenty high pulses. I was a little worried about that from the standpoint of conservation, but you see the energy transport in the pulse goes as p squared, and the exponential integral is integrable in the square. So it's p squared is integrable, energy is conserved, but you can get very high amplitude pulses. And so it goes on. This is a phase shift of 45 degrees, angle of incidence 74, phase shift of 60 degrees, angle of incidence 83, 75 degrees, angle of incidence 84, and this is the shape for glancing incidence, phase shift of 180 degrees. You simply have the mirror image rarefaction of the incident pulse. And you can see these positive reflected pulses here, but over here, where we're out at very long range, you see angle of incidence is 87 degrees. This is the surface reflection, this one here, and that is the bottom reflection as a rarefaction. So this is what's going on in your shallow water acoustics. If you start thinking about pulses, and you see the region that we're in is the region between where we were concerned with pressures of 100 more pounds per square inch, damaging things, and the region where you begin to think in terms of normal modes. This is the in-between, this is the connection. But I suggest that there are some bothersome things that you might, I don't know to what extent you thought about them and cultivated them, but broach some of the kind of thing kept arising back in the days when we were doing this and discussing it with others. See, people always want to think in terms of reflection coefficients. Now So you have an incident amplitude, you have a reflection amplitude, you have a reflection coefficient. If you have a reflected amplitude higher than your incident amplitude, you know, what about the meaning of reflection coefficients? You've got some ambiguity or paradox or whatever you like. Incidentally, as far as quantitative aspects are concerned, I failed to mention that. We took the ratio of acoustic velocities in the free water and the bottom to be 1.15, and we picked that pretty much on the basis of establishing the critical angle for total reflection. And that looked like 1.15, and that's what we used in making these calculations. We consulted Henry Stetson, who was then the world's leading expert on bottom sediments and their properties, and he told us that he took the density ratio around here to be 2.7, and so we used Henry Stetson's value for the ratio of the densities. And those are the numbers that went into this. Now, of course, at long range, this begins to show all of these effects that are going on. The surface reflection gets reflected from the bottom. The bottom reflection gets reflected from the surface. So, you know, you're heading toward normal modes. And so let me show you what, when you extend the mathematics, the formulas, it is very easily done. You know, you just you have the same shape, but you keep reapplying different phase, the same mathematical result, but different phase shifts because as you go out you have different angles of incidence. But that's very easily applied. And here is the kind of thing we would get. There's the experimental trace. This is angle of incidence are somewhere in the 80-degree range. But here's the theoretical curve, and here's the shape that we actually observe. And it goes on. This is an even greater angle of incidence. You can see the correspondences. And that was, in fact, astonishing. I mean, you know, that kind of...
Did you assume there was a waveguide, or did you just have a constant background? And
just constant background.
Well, that is
Most
a waveguide with the surface on the bottom.
But,
yeah,
Comprise a waveguide.
yeah, there's not a
Yeah.
profile.
There's no profile.
that's yeah. And there are deviations and discrepancies, but you know, a little bit of sea state and some undulation in the bottom and whatnot. But it's simple. It was astonishing. But, so that was the nature of the physics. It was a matter of recognizing the existence of the phase shift and applying it to the Fourier space.
What was the critical angle?
58 degrees.
So that first one was close to.
Right. That was deliberately close to the critical. 58 degrees was very close to the critical. Now, let me wind up with a brief look at the rest of the story. Because, astonishing as this seems to be, it's not quite right. Let me show you why it is not quite right. Now, there's nothing that seriously modifies the shapes that you see, but there is something else in the physics. And I'll be interested in the extent of awareness of this. So let me go back to fundamentals. Wave equation, which we take for granted governs this. But now, suppose we integrate that equation with respect to time. You see, what we're driving at in doing that is looking at what happens to the impulse in a pulse. Is the impulse delivered by an acoustic pulse, a pressure pulse, is simply the integral of P dt, the area under the impulsion. So let's integrate both sides of that equation with respect to time from 0 to infinity. All right. Over here, with civilized functions, we have the integral from 0 to infinity of the pressure time curve, the area under the curve, and I'll simply denote that by I. The impulse, Laplacian of the impulse. This plane wave. So that solution, which I've been showing you, is a plane wave solution. The source was always at infinity. And that didn't bother us at all. We had that agreement between the observed traces and the theoretical curves. But then along the line in there, I had a young undergraduate, a physics major, working in my group here. His name was Kenneth Wilson. He was the son of Wright Wilson, my old thesis advisor. And Kenneth Wilson, incidentally, was the 1982 Nobel laureate in physics for his discovery of the renormalization group. Well, at this point, somewhere in the early 60s, must have been late 50s, he was in my group here, and he called my attention to this. That the impulse has to obey Laplace's equation. And incidentally, the spatial distribution of the velocity of sound is irrelevant. I don't know whether you're aware. Have you?
You happy now?
Have people ever thought of that one? At first I thought that it was Kenneth who had discovered this, but then I was prowling around in treatises on waves and layered media, and I found this in a Russian monograph on waves and layered media. But that's the only other...
Okay, what if C is a function of T, though? What if C is a function of T?
Well, then you get in... That's a different ball of wax, yeah, right. But if you have a stationary distribution, it's this. Now, this is a serious constraint. And in the situation that we were talking about, you see where you have a point source if you're going to apply this, you can use the image method. And you apply the boundary condition, and you get an impulse out here, let's say. But according to this theorem, the impulse is never zero. Combining it, that's a total impulse, combining the incident and the reflected wave at this point. But the solution that I showed you, where glancing incidents, you get a mirror image, rarefaction reflect of the incident wave, that says that the incident impulse is zero. But this says it can't be zero. And this is what convinced us in the final analysis that the plane wave solution, although it's neat, gives you an insight, is incomplete. And that the real solution resides in solving the problem with a point source. Now that's a different kettle of fish. It's a much more complicated problem than the one we solved. But it has been solved. And I didn't have the mathematical horsepower to do that. And I threw that to my Amherst colleague, Dudley Town, who is a mathematical physicist, trained at Harvard. And we picked up an approach using Laplace transform, which had been developed for seismic studies by a Frenchman by the name of Cognard. That's right, treating it as a transient in Laplace transform. And when you do that, you get a complete solution. It gives all those shapes and everything. But what is missing, what completes the solution that the plane wave doesn't give, is the fact that you get a precursor. Because the higher velocity in the seabed, you get a very low amplitude precursor that contains all of the impulse that is missing in the plane wave solution. That's where it resides. So the complete solution has to be with a point source at a finite location. But the phase shift, the physics of the phase shift idea is perfectly valid. And this is the kind of thing that transpired. So that's the insight that we got out of this game. We've been looking for something entirely different, failed completely in that respect, and ended up with this, which was in many ways gratifying. So that's the nature of the story. If you want the references on this, I have it. You can pursue that to your heart's content.
Well, what journal is that in? That's great.
JASA, the Journal of Acoustical Society.
Probably right up there.
Probably.
The first paper is 1950, and the second one is 68. There's quite an interval. But we had to come to the realization that the plane wave solution was incomplete. We do have the whole story. Now, at the acoustic level, none of this is finite. And of course, no time variation in the sound velocity pattern, etc. But there we are. Okay, thank you.
That was great.
Now, I'm completely free. Most of you, those of you who are not, will not offend me in the least if you have to leave. But I'm perfectly willing to answer more questions and tell more stories if you like.
Well, we have the department lectures at 3:30 seminar in Smith. But some people might like to.
I think one difference with our group nowadays, we've been doing a lot of stuff where we measure from right close to the source out to infinity, but we look a lot at single frequencies. We haven't done a lot with pulses looking in the near field like that. So it's a little, your explosive work is a little different from
Yeah.
what we tend to do.
Yes, I realize that.
So that's, you have the time
You can do it,
part
I
that
mean,
we
some-
kind of factored out sometimes, but,
I have a question about, we synthesize pulses with these long transmissions of digitally encoded signals. Does that complicate this analysis? Does it complicate?
No, I mean, that's just, you're just looking at pulse compression there.
It's all linear, so.
But as
Yeah,
long,
it's
as
still
long as
linear.
it's linear, as long as it's relatively stationary over the length of the sequence, we're okay.
You can replicate all the physics.
You can replicate the physics. The thing I'm wondering is whether the techniques we're using to model these and then synthesize pulses out of this, basically do the Fourier synthesis that you're doing, whether or not we're seeing those and whether or not the models
right.
are necessarily giving us the right stuff out of that.
Yeah, I
Because
think your treatment of the pulse scattering is really interesting because
Yeah.
a lot of our work in long range acoustics was came out of the physics community. People like Roger Dash and Stan Flotte were working on the path integral, and the kind of acoustic equivalent to Planck's constant is 1 over the wave number. Right, so this sort of pulse propagation is something a little bit foreign maybe to physicists because we never think of integrating over some distribution of h bar in physics. And so we've been dealing with these sort of theories of scattering that they're telling us how close we are to getting to high scattering limits or weak scattering, and finding from observations that just the predictions are not telling us the right thing about
So they're
that approach.
They're monochromatic.
Right, and I've been looking forever to find some discussion of, this, scattering with pulse propagation. It's very hard to find any work in that area.
That's right. To come back to what was going on here at Woods Hole, for example, in the immediate post-war years, of course, the institution remained open full time. Work continued in all the areas. And the acoustics, where there was a big acoustics work under the group under the leadership of Brackett Hersey. He had Bureau of Ships money, and all of their work was in terms of frequencies. They didn't think in terms of pulses at all. Everything was essentially monochromatic. But the real world is not monochromatic, and
and you get very different results.
I kept urging Brackett to begin to have a look at pulses and see whether there. I don't know what can be drawn from that. I'm not expert in that field at all. But none of that ever happened in the acoustics group at that time. They continued everything in terms of frequencies.
Yeah, that's because it was driven by passive ASW considerations, I think.
Absolutely, sure, yeah.
Tone,
Yeah.
pure tone.
But that was the driving factor. But they tried to convey the idea that they were doing fundamental physics as well, that it wasn't just all ASW. And
Part of it now, and I think we're still driven by the same thing. I think part of it, we're still seeing the same thing. I think part of it is the ability to model to create acoustic models. The only wideband, quote, truly wideband acoustic model we have is ray tracing.
Yeah, sure. That's easy to use that way.
And that's
Yeah,
it.
sure.
And we can do we do
Fourier synthesis.
We do Fourier synthesis on the results of a bunch of narrowband models, but then, for instance, this data that we took out in San Diego, is surf zone data, doesn't show us, the actual physical data doesn't show us a precursor arriving to the main arrival, but if we do the Fourier synthesis of this is something we're trying to track down, you see it there, and but it's not there in our real data right now.
Yeah, well, that's good.
And but we're the only thing we have to use a truly wideband model is a ray trace. And that really doesn't capture. So you have this one model which is really deficient in the physics that it can capture,
Right.
and you have the narrowband models which can capture more of the
I
variability.
wouldn't say Ray modeling is deficient in physics.
Well, I better not get into frequency, it's fine.
There were a couple of things I noticed. You kept to kind of using the linear wave equation for your work, though, so nobody really had the nonlinear terms at that, you know. And then I guess the other thing is both the attenuation and dispersion were kind of unknown at that point too. That's what you were trying to capture with seeing the pulse shape there.
Exactly.
Yeah.
There were data beginning to appear on attenuation as a function of frequency.
Yeah, yeah.
And what I hoped I might capitalize on was applying that frequency data to the pulse.
Yeah.
And but never got anywhere. But that's exactly what I was after, because those data were just beginning to appear.
Yeah.
Now, was some of that work collaborative with the Naval Ordnance Lab at White Oak?
We were funded by the Naval Ordnance.
Okay.
It was NAVORD money.
In fact, was Yenny at White Oak?
He was my graduate student.
Oh, he was your graduate.
He was my graduate
Okay.
student at the time we did that work.
And Paul Fye came from there, didn't he?
He came. Paul Fye was in the group here during the war.
But didn't he come from the Naval Ordnance
That's
Lab?
right. Paul left here. He spent a year at the University of Tennessee in Knoxville, and then he became director. Then he went to BUORD in Silver Spring, and then he came here as director. Those were his steps. And the paper, the material that I showed you here is co-authored with Don Yenny, who was my graduate student at Stevens in the years immediately after the war. He went on to get a PhD under Yukawa at Columbia, and eventually he became professor at Minnesota and then professor at Cornell. But he went into particle physics.
Are you serious?
That's
incredible. Fantastic. Fantastic.
Small world.
Well, you might be interested to know that we're still working on that reflection problem. Reflection coefficient problem.
Well,
I can find it any day now.
Unscrambling the plane wave reflection coefficient from the point source measurement, and we've actually recently made some headway on that with a new student from Brazil.
Yeah.
I said, well, yeah,
It's a tough problem.
in deciding to talk about this to a group as on the leading edge as this one is, I was curious as to where I stood with this ancient history.
Yeah, very relevant.
I think there's
that agreement is beautiful.
sounds like very literal,
Just
bigger
taking
meaning.
the most basic pieces of physics and doing that nice
It's all
and
real.
Yeah.
I mean, right now, a lot of what we put our efforts into too is the inverse for the bottom. It's taking whatever type of data like that, try and find the properties from it.
But that's a key step. That's why we're doing it, because if you have the reflection coefficient, there are a number of inversion techniques that use that as input data.
But it's if you're playing.
Plane wave reflection coefficient. Yeah.
One
But that's what we're trying to do.
aspect I intended to mention didn't. This brings it up. See, we were getting away with treating the bottom as fluid, and that bothered me. But at some point or other there, I talked with Ewing about it, and Ewing just laughed. He said that in the work they were doing, they found that treating limestone as a fluid was better than trying to treat it as a solid. And
The thing you do have to worry about at low frequencies is the fact that there's actually a sound velocity gradient. Having a constant sound speed is not accurate.
Probably with an explosion, so high frequency.
Well, no, it has a low frequency component.
Low.
Oh, a lot of low.
Oh, yeah.
That's where all the energy.
Yeah. Although as you go to shallower and shallower angles, it's just tasting the top.
So where is
part.
the spectrum from an explosion is centered at what frequency? I mean, can you think of it as sort of
Depends.
a packet?
It depends on the depth, the weight of the charge,
Yeah, also it's a depth factor.
but it has a scalloped spectrum.
You,
20,
I mean, you 10, 20
Because of the
hertz,
bubble
you'll have a
pulse.
lot of energy. Way
Yeah.
I see. Okay. Wow.
Yeah.
But if you're concerned about precursors, you would want to treat it as a solid. Why would you treat limestone as a fluid?
It's not a property of the solid.
Well, you don't excite the shear modes.
Yeah. Yeah, if you don't like the shear modes,
It remains essentially a longitudinal pulse. I suspect that's the principle.
But there is some, I mean, if you're interacting with, I would think with limestone or some sort of hard rock, you will get conversion to shear. But in sediments, typically at a few hundred hertz, you can, in our experience, you can ignore the shear properties and do pretty well in reproducing.
well, it's pretty lossy,
Data.
is that right? The shear modes are pretty lossy, so.
Yeah, I mean, because there's a substantial difference in the velocities of all. You don't get good coupling into the shear, at least if you're talking about sediments. But I mean, you get the precursor associated with the head wave that's generated because the sound velocity in certain sediments is greater than the sound velocity in the water. That's what causes that. If you have a drop in sound speed, you don't have a critical angle, and that happens in soft sediments. But yeah, it's very interesting. That's great.
How far did you look to try to see the blunting of the shock front? You mentioned that earlier.
Yeah, how far in range?
Oh gosh, I'm not sure I remember I think more in terms of pressure amplitudes rather than ranges. It would have been a few pounds per square inch amplitude, which in range from size charge we were using, few pound charges would be out in some hundreds of yards, something like that.
Okay, so
The rule of thumb is kind of 100, 200 meters that I've heard.
because when you guys had shots like in the primer,
Yeah, we're way out.
you saw something that looked like a nice pulse to kind of coming in.
I mean, you can see just from his work. I mean, using the linear theory did a damn nice
Yeah,
job.
yeah,
You're up close
yeah.
and personal there.
Did you know that a few years ago they were blowing up stuff over on Shenandoah one day?
Possibly your old munitions.
They were,
we heard it was
getting rid of
Yeah,
it.
they're getting rid of it. Yeah, that was quite a few years.
Well, just maybe 5 or 6 years ago. One day, oops. Look out the window, there's a bunch of smoke.
Ranges of about 500 yards.
500 yards.
Must have been that same stuff.
It's interesting from a nonlinear standpoint. You might not expect the front to really blunt until it gets into a linear regime, because that dissipation at high frequency is sort of balanced by a flux of energy into the bore.
Yeah, I realize that, and but you see, by the time you get down to a few pounds per square inch amplitude, that feeding back is pretty small.
It goes okay.
And the viscous attenuation ought to be taking
over that. I see.
I had actually there was other work that we did during the war. Among that work was a look at the effect of sharpening under finite amplitude. And I calculated shock propagation velocities using what are called the Rankine-Hugoniot conditions. You satisfy the second law. And you don't do the dissipation in detail, but the results that you get for propagation velocity are the correct results, taking dissipation into account. So that kind of thing was done and published. Do you want the references?
Yeah.
On those?
Yeah.
Let me.
See if we can photocopy it.
This is a Journal of the Acoustical Society. The first paper is this one. Here, I'll give you one.
Could be playing right up there.
Maybe up there.
50.
Volume 22, page 231.
It's okay, don't worry. Actually, this year, Jeff will be completely archived on CD.
Yeah.
All the papers will be on CDs this year.
But the other one, 44, is that there?
Yes. A nice part of the school.
Yeah. The volume 44 one has the Conyard solution.
That was using the seismic community, right?
Yeah.
Yeah.
Conyard was doing seismology.
Yeah.
But he had a powerful approach, and it works. And of course, for the fluid situation, it's far more practical than the seismic one, obviously.
What was the bandwidth of the oscilloscope? I mean, how sharp a pulse would you see?
Well, the frequency response of the electronics, including the cables, which influence it, was up in the 30, 40 kilocycles.
So that's probably no problem.
So our frequency, that did not determine our frequency response.
Yeah.
Our frequency response was determined by the transit time across the gauge.
Really? From one end of the crystal to the other?
Oh.
Wow, okay. So, I see. So that was the fundamental.
That's the fundamental.
And that was what, a quarter inch?
About the large gauges we had to use for the low amplitudes were about an inch.
And that gives you some gain.
Yeah, the signal is directly proportional to the area of the crystal. And what we did was to pile up, as I had four plates in parallel. You connect them, so you have a basic area 4 times this area.
Yeah.
But the response was determined by the transit time across that.
Ask you a little different question. How did you drift into physical oceanography?
Well, being here, and as time went by, going to colloquy, that was the heyday, the flowering of physical oceanography. And I had an office next to Hank Stump. By that time, I was in the middle of the 3rd floor over on this side.
He was on the 3rd floor.
And we became close personal friends, and he kind of pulled me in. It was very easy.
Yeah, one-way interactions.
Another close friend was Al Woodcock, whom we've just been talking about here, and Al was working on sea salt nuclei and the atmosphere and so on. You know Woodcock's history? No. Al Woodcock drifted. He never finished high school in Georgia. He drifted in here somehow or other, at the time that Columbus was going to go over to Copenhagen and bring back the Atlantis in the early 30s. And he got himself hired as a deckhand on the Atlantis and participated in bringing her over on the first voyage. And Al was always looking at what was going on around him. He began watching the soaring of seagulls and began to discern that they were using the Langmuir circulation cells in their soaring patterns, and wrote a paper about that. And Columbus Iselin, who was very great on identifying people of that variety, among them Fritz Fugelister and Val Worthington. Fritz came out of the drafting room, you know.
Really?
Fritz came here during the war. He, an artist and musician. He had a young family. He wanted to stay out of the draft. He got hired in the drafting room.
Different kind of
He was drafted, yeah.
Well, I had read he was painting a mural in the post office somewhere. Hired.
The Woodcock, Fritz and Val both had some academic background. Woodcock had none whatsoever. And but he did that kind of thing. Columbus recognized a real naturalist of the Agassiz variety. You know, that's what Woodcock is. And then at the end of the war, Al decided to go into the sea salt nuclei problem in connection with weather, and proceeded to investigate sea salt nuclei. And I became friendly with him. Al was a wonderful guy, and a facility that I don't possess. You see, he'd look at things that I simply didn't see until he said, "Look." But he needed certain kinds of help. He was looking at distribution of sea salt nuclei sizes. So he had a kind of histogram in which he had nuclei of so many micrograms, and nuclei this, nuclei that. And so I finally said to Al once, I said, "But Al, there aren't any nuclei that are 10 micrograms." And he looked at me and he said, "Yeah, that's what Langmuir says." Well, I was never able to get him to understand the distribution function. That simply didn't work. But he did understand a cumulative distribution. So he finally presented his results with a cumulative distribution rather than a distribution function.
Right.
So it was that, and though in connection with that, I had one of my students we did 2 jobs. We did high-speed photography of bubbles bursting at a water surface and projecting nuclei. And we also did some accurate measurements on the vapor pressure of different concentrations of seawater, all the way down to, very high evaporated concentration. The reason for that was that we wanted to be able to calculate the growth rates starting with dry nucleus and going on to saturation. And I did that, among other things. Charlie Keith did observations of nuclei growth under a microscope, so he had numeric data. And I did a theoretical prediction of the growth rates that jive nicely with the observations. but we needed the accurate vapor pressures for that, for example. So all of this kind of thing.
What was Val Worthington's background?
I don't remember in detail. He also was in the drafting room. Prior to that, I don't know.
You can get pictures of it.
Do you think that sort of thing can still happen today?
No.
I don't think so.
No, that was an artifact of the times. And there wasn't anybody trained in oceanography. You know, Hank Stommel had an undergraduate background in astronomy at Yale. He never got a doctor's degree.
So you wouldn't get hired
But
John Ewing also passed away.
In those years, a few years after the end of the war, Hank, he was still around here, dabbling in various things. He went to Ray Montgomery and asked him what would be a good problem in physical oceanography, and Ray said the Gulf Stream.
So he did the rest. So I saw
the rest is history.
So Hank did the Gulf Stream with that, the insight that it was the sphericity of the Earth, the variation in the Coriolis parameter that produced the asymmetry. Prior to that, nobody had done that kind of thing. And of course, Hank had a very low-powered mathematical background. The high-powered people, Walter Monk and George Carrier, those people came in after Hank's paper and cleaned up the business with more high-powered mathematics. But the real insight
was there already.
Was Hank Stommel. And but that was the climate, that was the nature of it. All this kind of thing going on in the hands of people completely new to the field, who nowadays wouldn't make the grade at all, wouldn't be able to get in. And it was the flowering of post-war physical oceanography. It was an exhilarating time.
Yeah.
Do you have much interaction with Walter Monk?
Not much.
Worked with him.
I've met him many times personally.
Well, he was never here.
He was never here. He was always in Scripps.
Okay.
He visited, of course.
Yeah, he was telling me how he'd come out here for winters. I can't remember if it was before the war or after the war. He was here for a year, he said.
For winters?
Yeah, he was here whole winter. Yeah.
Okay.
And then he was smart.
He get tired of the sunshine.
He said they had a mean martini lunch up there in the fountain somewhere they go.
I'm sure they still
Yeah.
do. What was the funding climate like at that time? Because that's an issue that we all have to deal with these days.
During the war, it was pretty good.
Well, during the war, there was the funding. The explosives group was funded by WHOI. It started with MDRC, but WHOI took it over.
And there was a block of money. Did you have to write proposals yourself?
The director. I was a very junior member. I remember, and precisely what the director did, I don't know, but he did not write long, detailed proposals.
There you go.
The money
The
was.
National Science Foundation didn't even exist.
It didn't exist until 1950. Now that was well after the war, and Buord funded us and continued my work after the war. Ships funded Brackett Hersey and the Acoustics book, and ONR funded physical oceanography. So Columbus had in his pocket a block grant from ONR, and if you wanted to do something, you came into this office where Columbus sat, right here where I'm sitting, and told him what you wanted to do, and he'd listen, and sure, go ahead. And if somebody wanted a month of Atlantis time,
I went over to one desk.
it was a golden age, which could not possibly last.
It's a transient, just like your spikes.
Right.
It's
It's
non-linear.
it's interesting to have been a part of it.
Yeah, that's great. Well, you'll have to come back and give another talk. This was great.
Actually, that's one thing I think our department should think about. We have a lot of different disciplines on it.
Right.
Yeah, you do, and I think that's great.
Yeah. We've, in a sense, reinvented the institution. Like Gagosian mentions that, say, now, don't you keep reinventing the institution, because we have such a wonderful diversity of people crossing disciplines
Yeah,
in a powerful way.
I agree. You have an institute ready made.
Yes.
Where they are creating others.
How do we get on that topic?
What do you even institute?
The AOPD Institute.
I don't know how Barb will accept that statement.
Well, we can bring it up tomorrow during the meeting anyway.
Trace it back to an obsolescent trustee.
We'll just say we overruled you, Bob, the trustee.
That's right.
Okay.
Great.
Well,
Thank you.
thanks
Thank you
again.
very much.
Thanks very much.
Great.